Manuel, you are on mute.
Here, can you hear me?
Yes, we can hear you now.
Yeah, thank you. Okay, again, good morning, everyone. My name is Manuel Pérez-Carrasco, and I'm going to show you the work that I've been doing this year on my Spark postgrad fellow here at the Harvard Center for Astrophysics, along with the MethaneSAT team. This talk has two parts. The first part is about cloud and cloud shadows, and the second part is about plume segmentation, or at our segmentation task, and we solve both tasks using deep learning methods and machine learning. This is not working.
I think once you click in that window, then it'll start working.
Okay, so let's start from the beginning. Why methane matter? Why do we care about methane? Methane is a potent greenhouse gas responsible for more than 80 times more warming potential than CO2 during its 20 years of release. So a simple way to see this is CO2 decide how much warming do we have in the atmosphere, while methane decide how fast we get there. So if we cut methane emissions today, we can save us decades of warming. So this is why methane is one of the best targets for tackling climate change in the short term. And a good news about this is nearly 30% of methane emissions come from anthropogenic sources, come from oil and gas operations. Those oil and gas operations usually release methane through broken pipes, from leakage, broken pipes, open valves, and those leakages are not on purpose. So they both, us and the companies, don't want to release this methane. This methane is useful. They sell the methane as natural gas. However, those leakages are hard to find. We are going to be discussing some techniques, particularly from measurements from satellites that can be used from finding those releases. So before that, I want to introduce how the big picture of satellite monitoring using satellite monitoring is. The satellite monitoring usually can be categorized in two kinds. The first are global mappers, such as AstroAI, that can see the whole planet every day, but pixels are several kilometers wide. So they can tell what region it is emitting a lot of methane, but they cannot tell you which facility it is emitting that amount of methane. So in contrast, there are some point source images such as GHGSat that can see single facilities in high detail. But the problem with those is the area, the coverage of those satellites is usually tiny. So it is difficult for them to locate at basin scale. So there is a gap in between those both global mappers and point source images. MethaneSAT was particularly built to tackle this gap. It was launched in 2024, and it observes basins at a basin scale of about 200 by 200 kilometers coverage. So it's super well coverage, and at a spatial resolution of 100 by 400 meters per pixel. It has also an airborne companion called MethaneAIR, which is an airborne that also look at a basin scale at 100 by 100 kilometers coverage at a finer spatial resolution of 25 meters per pixel. So both MethaneAIR and MethaneSAT generate data in different levels of processing. The first level of processing is the calibrated, corrected, and georeference data, which represent the hyperspectral cubes where we have the images at each wavelength. So in this hyperspectral cube, each band represents a different wavelength in the spectrum. The second level of processing converts this light into gas amount using physical retrieval along with other derived products such as surface pressure, which are useful for creating cloud products. We are going to be talking why we want to create these cloud products in the following slide, but this is going to be a topic of an important topic in this talk. The third level of processing convert this gas amount into methane concentrations and generate column average prime fractions of methane, which is basically the parts per billion of methane we have in that particular space. So we have two important segmentation problems that I want to emphasize here. The first is we want to obtain cloud and shadows, and then we want to obtain methane mask in order to find where the liquids are being released. Here you can see two images, one from MethaneSAT and the other one from MethaneAIR, are the native pixel resolution covering the showing the full coverage of both instruments. As you can see here, you can clearly notice these white spaces here. Those are clouds. Clouds occupy a huge portion of each of the images, and those are problems. Why clouds are problems? Clouds are problems because pixels that are cloudy, with clouds, we cannot see the ground. So we cannot retrieve the methane signal if we cannot see through the cloud. And also shadows are other important artifact we need to remove here, because they usually distort the light path and also create an opaque signal that generates wrong numbers in our retrievals. So one important prerequisite in order to retrieve methane is to first being able to mask out both the clouds and the cloud shadows. And this is what we are going to be talking about, how we can use machine learning models for that. So for doing that, first we collect data. We had 500 hyperspectral samples from MethaneAIR, 200 or almost 300 hyperspectral samples from MethaneSAT. Both cover similar spectral range. They are very similar instruments from 1.68 to 1.58 to 1.68 microns, both with more than 1,000 spectral beams or spectral channels. So we have super good spectral resolution. The difference between both guys is very subtle. For MethaneAIR, we have cloud shadows, dark surface, and background. And from MethaneAIR, we only have cloud shadows and background, but the task is very similar between both. So a way to tackle this problem is, for example, tackling from the spectral perspective. We can take each pixel individually and take the full spectrum and use machine learning models, such as, for example, logistic regression or a neural network, in order to decide if a pixel it is a cloud or a shadow, and classify the pixel. This is good, this is fast, easy to train, but each pixel decides alone. So the problem with that is we are not taking into account neighboring pixels that are also giving information for the current pixel, and therefore we can generate noisy predictions. A way to tackle this is using spatial information, where we take into account neighboring pixels. So we can use convolutional neural network. We pass a kernel that computes the dot product between each pixel and at each wavelength in order to generate feature maps. Those feature maps are passed through an autoencoder architecture, and we can generate finally a prediction maps. Those prediction maps are usually more spatially coherent, but one problem of this kind of approach are the amount of parameters we require to train them, and also because we have some bands, some wavelets that are more important than others in order to classify certain atmospheric artifacts. And we have no possibility to tell to this kind of model what bands are more important than other bands. And that motivates our proposed method, which is the Spectral Channel Attention Network, or SCAN. And what we do here is to take the hyperspectral cues, average them across the spatial dimensions. So we have one value for each wavelet, and we pass those values through an MLP with a sigmoid activation function at the end. This activation function, what it does is to bound the output between 0 and 1, and this output represents our spectral channel attention. If the values are higher, we want to highlight that specific wavelet. If the values are lower, we want to suppress the information from that wavelet. So we multiply this by the original spectral signature, and we obtain a spectral and weighted average spectral signature that can pass through an MLP and then be classified, and that it could be useful, okay? Also, we can combine both spectral and spatial characteristic. An easy way, and I work to do it, is using ensemble approaches. So what we did was to take a train unit architecture and a train scan, use their output, combine them, and then pass it through a neural network or a convolutional neural network that decides the final output, taking both into account. So here you can see the results. First, this is the run through. Here for logistic regression and MLP, we have good boundary delineation, but we have a lot of noise in the predictions. Scan reduced the amount of noise in those predictions, and it also has good boundary delineation, but we still have some noise in the predictions. Unit, in contrast, reduce or suppress almost completely that noise and generate better spatial consistency on the predictions, but tends to over-predict the boundaries of the classes. When we combine both, using our combined approach with a CNN on top, we get best of both worlds. We get good boundary delineation with good spatial coherence. So individual method, unit is the best one for MethaneAIR. The scan method is the best one for MethaneSAT, but the combined CNN is the best one overall for all the settings. Also, an important thing that I want to just show you briefly is we compare this scan approach against classic or state-of-the-art methods that use self-attention. Those are the most used method nowadays. And we see that our scan method is better than those methods by 9 to 11 points of F1 score using only these 262 samples, which is quite great. So we pass through, we are going to go through the methane plume predictions. For that task, as I told you, we use this column, the gridded column average framework or fraction of methane, the amount of methane, the methane concentrations in parts per billion. The maps look like this. A thing that I want to emphasize for you to do not confuse, because here we have different spatial resolution that I mentioned before. And this is because the satellite collects each pixel as a spotlight. So we have more photons collected at the center of the camera, but spread in the edges. So if we can define a fixed grid in the latitude, longitude dimension, and we can see and count the amount of photons that it is in this latitude, longitude grid, and this is called oversample. And this both concentration maps are oversamples from the original data. So how we generate the data, how we collect data for creating plume mass, we use our wavelet plume finder method. This method uses a 2D wavelet transform applied directly to our L3 data. And what this method does is to decompose the data, the original signal, into two sub-signals, one containing most of the information, the fine-grained details of the signal, here the methane, and the other one contains coarser artifacts within the images and mostly captures noise. So if we subtract the image with most of signals with the noise, we can have an enhanced image that we can denoise, and we can, from this denoise image, use a threshold approach, such as, for example, above that concentration values, we are going to define a plume here, okay? So quite good. This worked pretty well. Also, there are some filters that are applied that ensures that these masks are physically possible, such as this mask should be consistent with the wind direction, and also the shape of the mask, the methane mask, is also possible. It is not physically not possible. We are going to talk a little bit more about this later. But the problem with this approach, despite it's great, it is we have to tune those parameters by hand. Usually the threshold has to be tuned by hand. The consistency with the wind direction has to be tuned by hand, so that this method does not scale into an operational setting and the full MethaneSAT archive. So we collected the data. We collected from 80 scenes from MethaneAIR, approximately 100 annotated plumes, which is great. We have quite good amount of data for MethaneAIR. From MethaneSAT, from 25 scenes, we collected just 100 annotated plumes. Usually, the deep learning methods require from various hundreds to thousand or millions annotated data. We only have 100, so it is here we have a difficult problem to deal with. And we also collected some simulated data generated by WRF LES method, and it is injected directly into real MethaneSAT scenes. And we collected 185 annotated plumes. So there are some challenges. I mentioned one, the amount of data. We have few labeled data. This kind of methods usually are trained on large amount of data. So this is something we need to care about. Also, we have full scenes, we have full basins, and usually the methods are trained from patches, fixed size patches from a particular image, and we need, when we do inference, generalize across the full image, not only patches. And we don't know really where the plumes are, so we cannot locate a patch and predict on those patch in the image. We have to predict across the full image, and from the prediction across the full image, generate a consistent output prediction. So we are going to be talking about those challenges and how we solve it. First of all, what the kind of segmentation we have talked up to now is semantic segmentation, which is basically pixel by pixel classification. So for example, if we are classifying person versus background, each pixel in the image belongs to one of both, or background or a person. But in contrast, instant segmentation is a mixture between semantic segmentation and detection. So we do not only classify the pixel into the respective class, but we also detect individual instances of the class of interest across the image. So we do not only detect person or not person, but we are able to individualize the person. And this is very important for the MethaneSAT setting, because we want to locate which facilities are emitting. And if we have two facilities co-emitting very close each other, we are going to mix the plumes, and we need to figure out what is the facility that is emitting which plume. So this is more useful than the semantic segmentation. So it will be cool to have a method using this approach. So how this approach works? Basically, we take the input image, we pass it through a backbone that can be a classic ResNet 50 backbone or a vision transformer, whatever neural network we want to use as backbone here, and we generate regions of interest. Those regions of interest are aligned. That means they are interpolated into a fixed size, and they pass through two branches, a segmentation branch and a detection branch. The segmentation branch classifies pixel by pixel, but the detection branch assigns a class probability of that particular object being to some particular class, and also the bounding box of that individualized instance or class of interest. So as I say, we use both ResNet 50 Vision Transformer. We also use self-supervised approach called MaskRCNN in order to see if pre-training our backbone on a different task it is useful for us. And here are the results. As you can see here, for both MethaneAIR and MethaneSAT, the MaskRCNN with the ResNet backbone architecture is the best performing one. This is completely out of the box without any trick, just raw predictions from each of the models are compared against each other. And an important thing you can notice here is all the MaskRCNN approaches are better than the unit approach in our case, but the ResNet 50 is the best performing overall. And as you can see here, this approach is the best at generating the boundaries around the plume. What unit tends to do is to over-predict the boundaries of the plumes, and what the MaskRCNN with the transformer backbone usually generates large amount of false positives in the images. So great, we have a model that also operationally is useful because we can individualize. This is great, but yeah, we have data from MethaneAIR we can take advantage of. So we have 1,000 labeled plumes from MethaneAIR that we can use in order to improve the model we train on MethaneSAT. So an intuition is both MethaneAIR and MethaneSAT use the same retrieval method, the same retrieval approach in order to generate the methane concentrations. So training a model using one of them using MethaneAIR could help the method train on MethaneSAT in order to improve the performance. So what we do is to first pre-train on the MethaneAIR data. So we generate a pre-trained method that already has some knowledge about what a plume is, what the shape of, how the shape of the plumes are. And what we do next is to adapt this trained model on MethaneAIR to the MethaneSAT images. And we took three approaches because, as I mentioned before, we also generate synthetic data. So we wanted to see if MethaneAIR data alone is enough, or we can also take advantage of this synthetic data. So one approach is fine tuning, which is basically we take the MethaneAIR trained model and we keep training, but only on MethaneSAT and see what happens after the training. Other approach is joint training, which we train both together the synthetic data along with the MethaneSAT data into the same model in order to see if adding that data help the model to improve the performance. And curriculum learning, in which we start with a lot of synthetic data, just a few real data, and we start to increase the amount of real data and decrease the amount of synthetic data while training. So we make the network to learn more easy characteristics on the synthetic data first, and then to adapt to the real, more harder scenario later. How it works? Pretty well. One thing that is not noticeable here is we are able to find all the true positives, which is quite cool. The three methods, both including using the MethaneAIR data alone or using the synthetic data along with the MethaneSAT data, are able to find all the true positives. False positives also get reduced from 63 false positive to 15, so or 23. So we could buy one fourth or 1/3 the amount of false positives. But the best performing model overall is this fine-tuning method, which we obtain 50 false positives. So this is quite interesting. And the hard part is then to generalize across full scenes. Okay, so what we do in order to generalize across full scenes is first take the full scenes and pass a sliding window across this full scene with overlap, 75% of overlaps. So we have a lot of different patches on these sliding windows, and we accumulate a lot of different predictions on each of these patches. What we do on those predictions that as you can see here, accumulates on the methane concentrations is to apply a confidence threshold and a non-maximum suppression. And what those methods that are doing is basically retain the most likely predictions from the model. So we retain only high probability predictions from the model, and we suppress the rest of the predictions. Something like this. We call this the baseline because this is something that a lot of detector models usually do, so it is not novel. But what is novel is we apply then a high sensitivity filter in order to further reduce the amount of true positives. And what this filter does is to first apply a shape filter, which try to remove predictions that are not physically possible, such as these spider shape predictions. So as you can see here, this spider shape prediction, it is not possible because the wind cannot spread the plume in that particular shape. So we apply a method coming from the wavelet method that also applies the same technique in order to remove these kind of things. And the idea is to preserve only real wine plume shapes. Then we apply another classifier, which is called the QND classifier, which applies some knowledge or expert knowledge to the plume. So here we have a plot on the methane concentrations against the albedo. And when you and this is this plot contain only data inside the plume, the concentration inside the plume. So we are plotting against in the plume region. So the plumes that are real plumes usually contain this shape here, this particular like horn on the predictions. So what this method does is to fit a polynomial on this shape, on this relationship between albedo and methane concentrations, and use the descriptors of that polynomial to train a machine learning model, a random forest, or a logistic regression in order to classify if it is indeed a real plume or a fake plume. So it used expert knowledge for that. One cool thing of this method, it is zero shot. It was trained on MethaneAIR, and we apply it on MethaneSAT, and it is useful for remove the spurious predictions, despite has not been trained on MethaneSAT. So how good those high sensitivity and high precision method perform? Indeed, pretty well. We decide to release our method in 3 modes. One mode is the baseline mode, which I already showed, with just filtering using classic techniques for filtering. The high sensitivity approach, where we apply the filtering, the spatial merging and the shape filtering. It is able to reduce the amount of false positive from 15 to 8, so almost a half. This is quite cool. But we still have some false positive. But we release this method that still have some false positive because those can be indeed plumes. And if we have other overpasses of the satellite on the same zone and we are predicting the same, we can retain those predictions and compare across time and indeed see if the prediction repeats in the same space, and if it repeats, maybe it means there is a real prediction. So we have no hard run through here. So the high precision mode, it is a mode that increases the precision such that almost every plume we predicted is indeed a real plume. So the amount of false positive is 1. This is, we lose some real plumes. So we have 7 false negative here that tell us that we are missing real plumes in our prediction, but almost every plume we found is indeed a real plume. So this is quite great, and every person that uses the model can decide if they want high sensitivity or high precision mode in order to evaluate their pipeline. A cool thing is we also analyze the false positives. Our method out of the box, it is generating almost 60% of our prediction were small enhancement that, as you can see here, you can notice something, you can notice some enhancement, methane enhancement there, but we cannot surely say this is a leakage from a facility, so it's hard to judge. And the 20% are cloud artifacts that not well removed. But one of my favorite discoveries is indeed after revision, we found a real plume that was indeed missed by the wavelet method, the method we use for generating our labels, and our method is capturing in this grand rule that the wavelet method missed. And this is quite fantastic. And also we have some predictions that we are still not sure about. We have produced significant work that you can see here. We presented in the NeoRIPS 2025 workshop for tackling the climate change in ATU 2025. Here at the AstroAI workshop, and we produce a journal paper at the IEEE TGRS journal, and we have a second paper on the Plume segmentation that is now under review. Here you can scan and you can see a blog post where we release all the material, data, and code. Everything is available and everything is full reproducible. I want to end with a bigger picture and some updates about the mission. On June of 2025, MethaneSAT lost contact after 14 months of generating data, but the data is not gone. So we have some data that the mission collected in those 14 months. And it is indeed a very valuable data. It is a data that, as I mentioned before, it is tackling an observing gap that no other instrument is able to tackle. It is observing at a resolution no other instrument it is able to look at. And this record exists and it is unique because we cannot get more. So it is invaluable and irreplaceable. And the approaches we already developed are the way we have for still generating science from this data. And also something that I want to emphasize is all the recipient methods we have used here are not strictly fit to MethaneSAT. They can be transferable to any other mission targeting methane or other pollutants, such as AstroAI, Carbon Mapper, Emit, or any other instrument targeting methane or next generation of instruments. So it's quite cool. And just to conclude, we generate a scan, which is the spectral attention method that indeed it is able to find some methane signatures in the spectrum that it is small and it is interpretable, and it is better than some of the current state-of-the-art methods out there, such as self-attention methods that are usually the state-of-the-art. And also we have a plume detection method that uses instant segmentation that allows us for source attribution. We can target at facility instances, and we discovered that and we showed that cross-sensor transfer techniques such as fine-tuning are able to recover almost all true positive. Finally, we released these two modes of our method, the high sensitivity and high precision mode for creating full screens of the data across different time lapse, and a high precision mode that helps for attribution and usually don't have a huge amount of false positives. So with that, I conclude my talk. Very happy to receive all your questions.
Wonderful talk.
Hey.
Thank you, Manuel. Okay, I'll ask two questions. One is, so you mentioned you have like different modes, right? Like the high precision, low. Is there any way you could imagine, you don't have to do it, but like to report a probability for each of the plumes so people can choose their own sensitivity?
Yeah, indeed, the method out of the box, it is generating confidence in this branch here. So this class is indeed a probability class. So what we do is to mix this class with also this probability map, because from the convolutional neural network that generate the segmentation output, we also have some probability maps. So we have two kinds of probability here: the probability given by the detector and the probability given by the segmentation branch. So we indeed in our paper report a probability of something being a plume or not as a weighted average between both this detection probability and this segmentation probability together. And yeah, we saw that indeed there is some correlation between the amount, the concentration of methane and this probability. They correlate pretty well. We still don't know what these probabilities are useful for, because yeah, here if you want to find discrete plumes, I think it is better to use the approach we took. But yeah, we are also providing these kind of probability maps that can be useful for downstream task applications.
Okay, can I ask another question? Okay, I'll ask one more question. So you have all these different stages, which seems like they could be useful for other tasks as well. Do you have any thoughts on the fact that you need all the stages versus just having one model? You know, because you're saying, okay, we're detecting the horns and things like that, which you would imagine maybe image models are good at finding those artifacts.
Yeah, I mean, we have different stages because we figure out that those stages jointly are helpful for generating the results we wanted to have in order to say, okay, this is useful. But indeed, you can use also the model out of the box. And the problem with that, as you can see here, is if we use this model out of the box, the amount of false positives is very high. We have 63 false positives with only 18 true positives. So yeah, the amount of false positives versus the amount of true positives makes this model not good, not reliable. So yeah, at the end we discovered that using these three things jointly help us to generate some reliability that makes our model useful.
Okay, thank you.
This is awesome stuff. This is really cool. I have a question about your activation vector or map or whatever you call it. I forgot exactly what you called it, but in the scan method.
Yeah.
Seems like there's some really interesting, cool physics in there that's being like embedded in there in some way.
Yeah.
Have you looked at that latent space? Have you like run a view map on it and see if water vapor like clumps together and methane clumps together and things like that?
Yeah, for cloud and shadows, we look at it, but it was hard for us to judge what is indeed looking, because we are looking with this method, cloud and cloud shadows. But now we are trying to use these methods in our current work in order to directly predict the methane plumes from the L1B data without passing for the L3 data, which is the obvious next step. And when looking at the spatial attention with the methane transmittance at each wavelet, we can see that there are some peaks that indeed match with the methane transmittance. So for example, this, we have a peak here, we have a peak here where this signal is strong. Also, we have a lot of peaks in this part here where we have a lot of absorption of methane. So yeah, it seems like the places where we have peaks indeed are places where the methane is absorbed, which is, I think, quite cool. So,
Thanks.
Thanks for the talk. Can you go into the like forward a bit, the slide where you have multiple image like the detection versus like the one you generate with the fuel?
this one?
I think a bit before that one. Oh yeah, that one that had the purple square in the middle, that one. Yeah. So I don't do AI, so that's why I not understand this very well. But what's the difference between original image and input image?
Yeah, this is indeed here is nothing of AI. This is the method we use for generating the labels. So this is the original image, and something you want to do for generating the labels is somehow remove the noise and try to see clearly where the methane plume is. So this 2D wavelet transform, what it does is to convert this noisy data into two versions of the data, a version with enhanced signal, and a version that contains more coarser characteristics such as the noise. So then, using these details and the noise image here, we can subtract the full detail image with the noise, and this subtracted image contain more information or more enhanced signal from the methane concentrations. So then we can apply basic denoising algorithms, and here we can see a clear plume structure after doing that. And with this, we can directly apply something like a threshold on the concentration values and say, okay, above this certain threshold, we have a methane plume or not. So indeed, what we do here is basically try to enhance the methane concentrations in order to automatically, data-driven, try to generate this threshold and filter what it is plume, what it is not plume.
Thank you.
Thanks for the great talk. So on the same topic, for the reconstructed image, how do you prevent it from reconstructing the plume also? Do you set like a lower bound, a lower that?
Yeah, I am not in full details of this work for generating the plumes, but this comes directly from these two wavelet transform. So we need to set the parameters of these two wavelet transform, which it is also one of the limitations. A lot of things have to be tuned for this method to work. There are parameters involved in this transformation, and also there are parameters involved in the mask creation, such as the threshold, that indeed are makes that this method require a lot of visual inspection and manual parameter tuning. And this is why we wanted to create this deep learning approach for automatize this task, because this method is cool, but we need to manually tune each of these parameters in order to avoid these kind of issues, and that does not scale into full pipeline or full operational setting.
Thank you. Any other questions? Cool. Well, let's thank them all again.
Thank you.